Dad, how did this get here? Didn't we just order it like a few hours ago?
When my older daughter asked that, I stopped for a second because it is a simple question with a surprisingly deep answer. Somewhere between a tap on a screen and a box on our doorstep, invisible systems spin up, data races across networks, decisions get made in milliseconds, and the physical world moves. It's fascinating to think what happens when you stream a song, book a hotel room, reserve a flight, or open an app and just expect it to work. All this technology is so fun, and I love working in this industry. I've spent my career building software and systems that make up the internet. I was CTO at Shopify and ServiceNow, an SVP at Slack, an early engineer at Cisco Systems, and now I'm CTO at Webflow. I've helped build data centers, protocols, software, and services, and led global teams along the way. This podcast is for anyone who wants to understand how our modern world actually works, not just shopping and delivery, but the invisible machinery behind nearly everything we do. It is for anyone who's ever wondered, how did this get here? Or how did that actually happen? I'm excited to take you on a journey, to take these layers of technology apart and explain them in a clear, grounded way. You probably think you connect to Wi-Fi, you're on the internet, and away you go. Well, I wish it was that simple. I'm Alan Meinwand, and welcome to Pixels to Packages. Welcome back to Pixels to Packages. If this is your first time here, I'd encourage you to begin with episodes 1 and 2, because this story is deliberately layered. In episode 1, we slowed down the instant you tap a button and followed that request as it moved across networks and into a data center. In episode 2, we stayed inside the browser and examined how HTML, CSS, and JavaScript transformed return data into structure, style, and behavior, ultimately giving you pixels on a screen. This third chapter builds directly on those foundations. We're not leaving the details behind. We're stepping outward to see how many machines are actually involved when it feels like you're just talking to one. It's easy to imagine a straight line. You tap a button on the screen, a page loads. One action, one response. It feels as though your browser reached into a distant server in a distant building. That server performed some magical work and then sent something back. That version of the story is clean, it's intuitive, it's easy to understand. But unfortunately, it's also incomplete. Because that one tap is not one machine, not one rack, not even one data center. There are virtual IP addresses that represent services rather than specific pieces of hardware. There are load balancers accepting connections and making routing decisions in nanoseconds. There are rows of 19-inch servers stacked in racks, connected by fiber through high-speed switches that form local networks inside massive data center facilities. There are storage systems built from arrays of flash memory, and there are copies of content distributed across continents, positioned close to you before you ever ask for them. The simplicity you feel when you push that buy button and see those pixels is real. It's built on this global coordination of many, many systems. And today we widen the lens a bit, because I hate to break it to you, but there's no such thing as just one server. So far, Pixels to Packages has been moving in layers. In episode 1, we focused on movement. We traced the request from your laptop through your local network onto your internet service provider, across interconnected networks that form the global internet and into a data center. We talked about DNS, translating human-readable names into IP addresses. We talked about packets, the small units of data that carry every request. And we unpacked encapsulation, how application data is wrapped in layers from TCP to IP down to link level, and each layer performing a specific role. That episode was all about how information travels. And then in episode 2, we focused in on interpretation. We examined what happens after the information arrives. HTML defines structure, CSS defines presentation, JavaScript defines behavior. The browser sandbox isolates that for security. The rendering engine constructs the DOM model, the document object model, applies the styles, calculates the layout using the box model, and paints those pixels onto your screen. So that information was how information becomes a pixel experience. Across both episodes, we relied on a pretty simplifying assumption. We spoke about the server as if your browser is connected to one machine in one building. That machine processed the request and returned a response. That mental model is useful when you're assembling all the pieces. It simplifies things. It helps you understand cause and effects, and it keeps the story pretty understandable, something that even I can understand. But it's actually not how modern systems operate. At scale, there's rarely a single server. There are fleets of servers, rows and rows of them. There are layers of systems whose sole responsibility is deciding which machine should handle your request. There are internal networks inside the data centers that resemble the network in your house, except for they operate at radically different scale, with fiber links instead of Wi-Fi, and switches capable of moving enormous volumes of data every second. So today we shift from a single machine mindset to a distributed systems mindset. Not abstract theory and academic diagrams, but the real infrastructure that makes every tap feel simple. So let's go back and start at the moment your browser finishes its DNS lookup. DNS returns an IP address. The browser initiates a TCP connection to that IP address. And from your browser's perspective, it's talking directly to whatever owns that IP address. But in many modern architectures, that IP address is actually what's called a virtual IP address, often abbreviated VIP. A virtual IP address does not permanently belong to a single physical server, but it represents an endpoint, an abstraction, and that abstraction is typically built into what's called a load balancer. So when your browser establishes a TCP connection to the virtual IP, the load balancer receives that connection. In many configurations, the load balancer terminates the TCP session. So while we've been saying your browser talks to the server, it actually means that your browser talks to the TCP connection that ends at the load balancer. The load balancer then opens up another TCP connection to one of several servers in a server pool in the fleet. From there, the request is forwarded and processed. So think of it as like there's two TCP connections, browser to load balancer, which you don't really see because you think you're connecting to the website. But then the load balancer then sets up another TCP connection back to this fleet of servers. Now, there are variations in how this is implemented. Some load balancers operate at layer 4, so they distribute traffic based upon the IP address and the port. Others operate at layer 7, so they inspect the HTTP headers, making routing decisions based on host names or URLs or cookies. But the core idea is the same. Inbound connection from your browser to load balancer, and then a decision in terms of which server to hand it off to, either based upon an address or based upon another quality, a host name, a server, or response time. So what exactly is load balancer? What is this thing doing? At its simplest form, it distributes incoming requests across a fleet or a pool of servers. But that description is a little too simple. A load balancer is not just forwarding packets blindly. It actively participates in the connection. When your browser initiates a TCP session to what appears to be that single server, it's usually connecting to the virtual IP that represents the load balancer. The browser completes a full TCP session with the load balancer, not with the actual backend server, the server, as we've been talking about it, that processes the request and gives you the data back. The load balancer terminates the incoming TCP session. It closes it. It then removes the encapsulation. It pulls off the TCP. It looks at the TLS and the security. It makes sure that the right data is there. And then it sets up another TCP connection. So it starts over again and re-encapsulates that data and sends it off to one of the servers. So a second TCP connection exists between the load balancer and the server it selects. Because there are two separate sessions, the load balancer maintains an internal, what's called translation table. This table tracks which client connection, which browser connection, maps to which backend connection. So every packet that arrives from your browser is associated with a specific connection between the load balancer and a server. Every response from that server is mapped back directly to the client-side session inside the load balancer. Without this state tracking, the responses wouldn't reliably return to the correct browser, to your correct screen, and get you the right pixels. This is all very fault tolerant and happening in virtually real time. So what's happening is, think of it this way. A connection comes from your browser to the load balancer. The load balancer is continuously monitoring the health of all the servers in the fleet, all the servers in the pool that could answer your question and could give you the data you need to produce those pixels on your screen. It performs periodic checks, it checks the load, and then it sets up a connection to one of those servers that will surface your request. If the server fails, the load balancer realizes this and removes it from the pool, it removes it from the fleet, and it won't send any more connections to it. So a big advantage of load balancers is that you can actually do maintenance on the servers in the fleet, take them up, take them down, and sessions don't break. So there isn't a single server that's handling all the requests. Again, there's a pool of servers, and the load balancer is acting as a proxy in the middle. It terminates the TCP connection from your browser, and then it sets up a connection to one of the servers that's healthy and able to handle your request. Load balancers also manage capacity. If traffic increases, you can add more servers to the pool. It also allows things to be removed from the pool. If traffic decreases, you can remove the set of fleet of servers in the pool as well. This scaling, where you scale things left and right, you think about adding servers to the pool in sort of a row, it's called horizontal scaling. So instead of relying on one very powerful server, systems scale by adding more systems and more machines and more servers. And the load balancer is the technology that allows you to do that and scale it horizontally. Now, at this point, an interesting question emerges. If the backend server is only connected to the load balancer, how does it know the real source IP address in your browser? Well, by default, the server in the pool will only see the IP address of the load balancer. From its perspective, it's seeing a TCP connection from the load balancer to it, because that is the immediate peer in the second TCP connection. Remember, the first TCP connection is your browser to the load balancer, the virtual IP. The second TCP connection is from the load balancer to the server in the pool or the fleet that is available, has the load, can handle your request. And the translation table is the thing that puts those two together. Now, there are a couple little tricks in here that can commonly be done. In HTTP systems, you can add a header called x_for, which contains the original client IP address. Because you can imagine that the server, the website, data itself might want to know where you actually are. Because based upon your actual source IP address, way back in the browser, way back at your house, it might want to send things in a certain language. It might want to send specific ads. It might want to give you offers to certain commerce that's available in certain products that are available in your region of the world. So knowing that IP address that is the source way back in your browser, way back in your home, is really important, even though the session that the server in the pool sees behind the load balancer comes directly from the load balancer. So you hear about things like x_for, client IP addresses. These are really so that the server in the pool can understand who actually initiated the request, even though the direct connection comes from the load balancer. Now, that was a lot, but there's many implementations of load balancers. Some are dedicated hardware appliances built for like really high performance networking. Many are software based. There's open source projects like HAProxy and Nginx that are widely deployed as load balancers. They are capable of handling enormous numbers of concurrent connections. Think tens of thousands or hundreds of thousands or millions of connections. They can route traffic again based upon DNS names, URLs, cookies, other data. They can enforce rate limits. They can provide visibility in traffic because they're seeing every connection coming from the browsers, terminated on load balancer, and then into one of the pool and the servers on the backside. And they can make routing decisions in milliseconds. Now, from the outside, from one side of the load balancer, everything looks like one big server. Inside the load balancer is two sets of TCP sessions, one to the browser, translation table, and then one doing health checks and connecting servers in the fleet and in the server pool. It's all about orchestration. It's all about scalability. It's all about horizontally scaling load. So when lots and lots of sessions come in to connect to the server, as we've been calling it in the past, it really isn't a server now. It's a load balancer with tens, hundreds of servers behind it, each taking individual sessions, each terminating their own TCP sessions, and each handling a portion of the load. Now that was virtually what's happening. So let's ground this a little bit in physical reality. A data center, as we've talked about, is a building filled with rows of metal racks. Each rack is typically 19 inches wide. It's an industry standard. And each side of each rack are these servers that are stacked vertically. Each server is a computer. It has CPUs, memory, storage, and network cards. On the top of the rack, there's usually a network switch, and each server connects to that switch, often using high-speed Ethernet over copper or fiber. The rack switch then connects to a higher level aggregation switch, which connects to the core of the data center network. This creates a hierarchy of switching, forming a local area network inside the data center. And that same local area network inside the data center is the network between the load balancer and the fleet of servers. If you remember episode 1, we talked about your home network. Your laptop connects to your Wi-Fi router. Devices in your home talk to each other through that router or switch. A data center is the exact same concept at just a much bigger scale. Instead of a few devices, there may be tens of thousands of servers. Instead of one router, there are layers of switches, which are what's called a networking fabric. Instead of short cables between your laptop and your home router, there are carefully managed bundles of fiber running between racks and rows. Every server in a rack is part of a local network, and every rack connects into a larger network fabric. And the load balancer is connected to that network as well. Database servers are connected to it, storage systems are connected to it. It's all about the connections between the servers, and the load balancer is a key part of that to direct traffic from your inbound request to the website to the right server, over the right fiber, over the right data center network to reach the right server, the right piece of storage. Now, your request travels through many distinct networks, as we're talking about here. From your device to your home network, from your home network to your internet service provider. There are many autonomous networks that form the internet, and then eventually you get to the data center edge, the data center internal switching fabric, to the load balancer, to the specific backend server. Every step along the way, there's a network. We're going to go much deeper into routing and networking design, if that's what you're into, because I am, in a future episode. But now the key idea is simple. Nothing talks to anything without a network connecting them. And your browser talking to a server crosses over multiple networks through a load balancer, and that load balancer uses another set of networks to connect up to the pool and the fleet of servers. Because the application server that ultimately handles your request, again, is rarely one. It's rarely self-contained. It may need to actually retrieve data from another server in the data center, like a database. That database itself may also consist of multiple machines behind another load balancer. It may access network-attached storage, backed by arrays of flash memory optimized for performance. It may call internal other services. So imagine your browser connects to the load balancer connects to a server, the server in turn sends you back the first page. And now you want to connect to a different service. Maybe you want to chat. Maybe you want to make a payment. Maybe you want to connect to a service that offers up a coupon. Maybe you want to do something that invokes a separate service on the site, like get a recommendation. The recommendation service might be running on a separate set of servers behind a separate load balancer. Each of these interactions generally occurs over the internal network in the data center. Each of these services, chat, get a coupon, make a payment, do something, pull back your previous orders and do something with one of those previous orders out of a database. Each of these interactions occurs, and each of them is a separate TCP connection, separate IP, separate routing, separate encapsulation, separate number of packets. I think you get the idea. It's all something that happens so quick. And from the outside, it looks like just one server responding. But inside, it's a choreography of systems, a choreography of services that to you is a bunch of pixels on the screen. Now, let's return to your browser. When you load a web page, the HTML, as we talked about, might come from a single origin, a server behind a load balancer. The JavaScript bundle might actually come from another domain, another service. Images may be stored on yet a third service. Fonts and analytics scripts come from a different place. Now you can see this. If you're so inclined, open up your browser's developer tools, click on the network tab, and reload any page. You're going to see dozens of requests, sometimes hundreds. Each request involves DNS resolution, connection establishment, data transfer. Each request may map to a different IP address, and each IP address may correspond to a different physical location. You know, you load a website up and sometimes things sort of pop on the screen differently. 9 times out of 10, those different sessions, those different items popping up on the screen are different connections coming from different locations, maybe different data centers, or maybe from a content delivery network or CDN. And CDNs play a critical role here. So in this next section, we're going to dive into a little bit about what a CDN is. A CDN is a globally distributed network of servers designed to cache and deliver content close to the user. Now, at its core, a CDN solves two basic problems: latency and scale. Because while we've been talking about connecting to a server or a set of servers behind a load balancer in a data center, again, there's another layer here. The other layer is that some of that content is pre-positioned, already built into servers that are closer to your browser. That solves the latency problem. Latency is delay between a request and a response. Between you hit the click, type in the website name, hit the icon to load something else, and the first response. The farther the data has to travel, the longer it takes. Even at the speed of light, distance matters. So every image, every style sheet, every script has to travel from an origin server or servers behind a load balancer to every user on the planet. And if all those came off a single location, the further you were from that origin, the slower the website would feel. So a CDN reduces that distance. Instead of serving every request from one location, static assets like images and pictures and CSS files and videos are often replicated to many locations around the world, hundreds and hundreds of locations around the world. These edge servers are often deployed in major metropolitan areas, inside of like internet exchange points that are close to your house, or directly within your internet service provider itself. So when your browser requests a static file, DNS can actually direct it to a nearby CDN edge node. So think of the servers in the data center behind the load balancer as like a core. And then think of all these little points, hundreds and hundreds of points that have cached copies of the content. And if DNS can find that cached copy close, it can respond in much lower latency. It doesn't need to contact the origin server back in the data center. And if the content isn't yet cached in one of these hundreds locations, the CDN can go grab it from the origin server behind the load balancer, pretending that it's a browser, and bring it to the CDN cache. Again, think about caching things like scripts, images, menu buttons, things that are fairly consistent for many, many users hitting a site. This dramatically does two things. It reduces the load on the origin to data center servers because not every request has to go there anymore. Some are being served by the edge, and it improves performance for users across the entire planet. But CDNs do more than cache content. Because the CDN sits in front of the origin servers, it's that edge network. It can also act as a protective layer. Now, instead of every request having to go to the load balancer, go to one of the servers in the pool, imagine if most of those requests can already be served by the CDN's network edge, the thing that's closer to you, that's right in your ISP. The CDN can inspect the request, filter out malicious traffic, and can handle things before they even go to the data center. And this is important for something called distributed denial of service, or DDoS attacks. You hear about DDoS attacks a lot. People talk about them. I don't think people really truly understand what they are. So what a DDoS attack is an attacker is attempting to overwhelm a system with a massive volume of traffic from many distributed sources. The goal is to exhaust the servers behind the load balancer, just make sure they can't handle any more requests. So imagine someone who sets up 100,000, a million systems across the planet, and now says, let's go attack, let's go load the content from this particular website. You can imagine that even with horizontal scaling, even with load balancers, it's very, very difficult to scale those up properly. So a well-designed CDN has this enormous capacity, and it can basically absorb all the traffic instead of having it go to a single data center. So if you're trying to go to Spotify.com or CNN.com or your favorite website, if a DDoS attack goes to that website and those assets are already in the hundreds of CDN nodes across the planet, that attack gets distributed across those nodes and the site stays up. So the CDN can detect abnormal traffic patterns, it can find things that are suspicious, and can actually block them. So the CDN becomes a shock absorber for that website. It can also do other things like filter traffic out, detect bots, see if things are actually trying to reach the same resource in a rapid succession that doesn't look like humans. It can do a lot of different things. And in the end, two users loading the same website from different continents might receive content from entirely different CDN servers. One may connect to a CDN node in New York, another one might connect to a CDN in Frankfurt. Both see the same page, and both are shielded and protected by the same distributed layer. The page looks identical. What's happening is your browser is reaching out to connect. It's trying to connect to Google. When it tries to connect to Google, it turns out that some of the content on that page, the images, maybe some of the links, are already in the CDN. Those come directly from the CDN, from the edge. They never actually go to Google. But the ones that actually do go to Google go behind a load balancer, into the fleet of servers, get distributed content. Now imagine that happening for millions and millions and millions of websites, and CDNs doing this in a way that scales dramatically for all of them. The infrastructure is delivering globally optimized, globally distributed, performance optimized service. And CDNs are actually a fundamental component of how the modern web delivers content reliably, securely, and at global scale. Again, if you want to see it, you want to see it in action, bring up a website, just your favorite one, go to View, and then go down to the Network tab, or view the source, and start looking for the HTTP requests, or start looking for the names, the DNS names in the actual source code. You'll find some come from a CDN, some come from an origin server, some come from other locations. Because again, while you think you're connecting to a single web page and a single site, you're actually connecting to a distributed system. Some of it's served from the CDN on the edge. Some of it's served from a pool of servers behind a load balancer in a data center. All of it requires networking. All of it happens faster than you can think about. So let's step back and look at the bigger picture, because I think that's really important. In episode 1, we showed you how packets move across networks. In episode 2, we showed you how the pixels get assembled, and those pixels show up from that code that gets delivered from the network. In this episode, we revealed what happens when you actually think you're connecting to one server, but you're actually connecting to a globally distributed system. Servers behind load balancers, or content coming from the network edge in form of a CDN. It's just amazing to see how all this works together. You're going to see this happen over and over and over again as we continue to go through this podcast. You're going to see how tap on a screen goes to packet. From packet goes to load balancer. As load balancer goes to server fleet and pulls a server. How server fleets use CDNs for global distribution. And how that content delivers to your browser and what you think is a single website through this vastly amazing globally distributed system. And we are still at the pixel stage. And eventually those pixels get triggered into actions in the physical world. Orders get placed, inventory systems are updated, warehouse management systems fire up and activate, robots travel around warehouses, packages travel in cardboard boxes, and they show up at your front door. If you think do you think the digital world is distributed? Wait until we step into the physical supply chain. There's no such thing as one server. There's actually no such thing, perhaps, as one warehouse. There are always systems behind the systems. And now you can really start to see them. You can really start to notice when the web page loads, multiple sessions, content coming from the edge, content coming from the data centers. It's a fascinating thing, and I can't wait to dive into it more with you. Thank you for joining me again on Pixels to Packages. See you on the next episode. We start to discuss another fascinating topic, and that is e commerce. Thanks again.